Okay, so here is the fifth and I believe final um, of my videos on special relativity. Okay, so what we've established so far is that what we've established in the previous video is that when an object is in motion, its mass appears to increase according to this. Okay, and gamma is 1 over the square root of 1 minus b squared over c squared. Okay, so now I want to give you a thought experiment. Okay, so thought experiment where we say, let's start off with two boxes. Okay, and each box has a mass of 1 kilogram. Okay, and there's a spring in between. It also has a mass of 1 kilogram. Okay, and initially these two things are at rest. Okay, no big deal. Or sorry, the three things are at rest. Okay, and then a force comes, some external force comes and pushes on the left box. And another external force comes and pushes on the right box, and it accelerates these boxes. Okay, so now we have a box here and a box here, and these are moving at we will say 0.6 times the speed of light. 0.6 speed of light. Okay, here's the spring still in the middle. The spring still has a mass of 1 kilogram. Okay, now for the two boxes, gamma equals 1 over square root 1 minus 0.6 squared. Okay, and if you do the math, what it turns out is gamma is equal to 1.25. So this box is now 1.25 kilograms, and this box is 1.25 kilograms. Now let's look at the total mass of the system. Okay, for this first state, okay, I'll call this state A. Okay, at state A, you've got two 1 kilogram boxes and a 1 kilogram spring. So the total mass is 3 kilograms. Okay, here now, in the second state, you've got two boxes, each at 1.25 kilograms. That makes 2.5 kilograms. And then you have the spring, okay, which is 1 kilogram. So in B, mass is 3.5 kilograms. Now, what about conservation of mass? Well, conservation laws all carry a condition on them. The condition is in a closed system, okay? This system, between A and B, it is not closed. There's an external force acting on each of the boxes. There are two external forces coming in between state A and state B. So the system is not closed between A and B. So conservation of mass is okay here, or non-conservation of mass is okay, I should say, because there's an external force, okay? But now let's look and see what happens when these two masses hit the spring. Let's say this is timed and set up so they hit the spring and, whoops, let's get rid of those dots I drew there, okay? And come to rest when the spring is mightily compressed, okay? So this comes back to rest, which means now it has a mass of 1 kilogram. This has a mass of 1 kilogram. The spring has a mass of what, okay? Because let's say the spring has a mass of 1 kilogram. Now C, we have a mass of 3 kilograms. Okay. And what I want to do now is basically go to state D. Okay, that'll be the last one, where they bounced off the spring. So this is when the spring is momentarily at rest. Everything's momentarily at rest, maximum compression of the spring. Now they bounced off. The spring is back to 1 kilogram. Maybe it was always 1 kilogram. Okay. This is 1.25 kilograms. Okay. This is, come on, there we go, 1.25 kilograms. Okay. 0.6C, 0.6C. Okay. So it's obvious now if the total system, the system at B and the system at D are different only in the direction of velocity of the boxes. Okay, so clearly their total mass has to be the same. Now the question is, what happens to the total mass in between? Okay, is this really what happens? Does the total mass go down to 3 kilograms and then back up to 3.5? And what I want to do is do something I call physics Mad Libs. Okay, so let me see if I can. I'm certain, almost guaranteed to fail this. No, don't do that. Let's see. I'll try to move everything to the right here. Yay! Okay, I did it. Okay. No, hold on. Okay. There we go. Boom. Okay, great. So I'm going to do what I call physics Mad Libs. So from A to B, okay, external force acts, or external forces act, boxes gain mass. Except everywhere I would write mass, I'm going to put a blank, okay? Now, from B to C, the boxes compress the spring. Boxes lose mass. Spring, what does it do? Mass, okay? There's a rhyme to it. There's a reason for this, okay? From C to D, boxes leave the spring. Maybe I should say spring pushes boxes, okay? Boxes gain blank, and the spring blank. Okay, let's say that we have conserved mass here. Okay, I want to try to show you how this can make sense. Let's say we have conserved mass here. So let's say that what happens here is as the boxes lose mass, the spring gains mass, and vice versa. Okay, maybe I didn't set this up the best way, but whatever, I'm committed. Okay, now just look at this here. Look at the stuff on the right-hand side and think back to, say, the end of first semester of physics or something like that, okay? If last winter or spring, before coronavirus and everything, I were to give you this thing and say, what goes in the blank? What would you say? You wouldn't say mass, because we didn't learn about all this stuff then, right? You would say something else. Another, not mass, but another scalar quantity. Energy. 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 Right? Because let's look at the first step, okay? From A to B, the external forces act on the boxes gain energy, right? Kinetic energy, okay? As the boxes compress the spring, the boxes lose energy, and the spring gains potential energy. And then when the boxes leave the spring gives that energy back to the boxes. So here's the thing. Mass and energy are basically the same thing. Okay? And so the answer is this is not 1 kilogram. This is 1.5 kilograms, so that you can have a total mass of 3.5 kilograms. Okay? Because it turns out that basically the gain in mass from an object going faster is actually its increase in energy, the kinetic energy it gains as a result of going that fast. And when the boxes hit the spring right here, what will actually happen is the spring will get heavier. The spring will get more massive because it's gaining potential energy. Wacky, okay? Now let me show you, let's see, new file, don't save. We're going to start over here. Well, I'll start with a blank screen, okay? And talk about now what happens when an object is moving at some speed. So let's say here's an object with a rest mass of m, and it's going at a speed of v, okay? So we have gamma equals 1 over square root 1 minus v squared over c squared, and its inertial mass is equal to gamma times m, okay? Equals gamma times, or sorry, not gamma, equals m times 1 over square root 1 minus v squared over c squared. How does this relate to the energy? Well, the energy is equal to m prime times c squared, okay? This is basically sort of where mc squared comes from. And what I want to do is take this, okay, take this expression here. So energy is going to be m prime times c squared, which means it's going to be m times c squared times 1 over square root 1 minus v squared over c squared. And I want to take this and see what this does. But it's hard to analyze a function like this. 1 over the square root of 1 minus v squared over c squared is hard to analyze. What is easier to do is basically do a Taylor series of it, okay? Now doing a Taylor series on v would be kind of a nightmare, but what we can do is we can define, I'm going to define w equals v squared over c squared, and then what we have is E equals mc squared times 1 minus w to the negative 1/2, right? Because w is v squared over c squared, so 1 minus v squared over c squared to the negative 1/2 is this, okay? So we can do that, okay? And then we can take derivatives with respect to w. So E at w equals 0 is going to be, well, this is just going to turn to 1. 1 to the negative 1/2 is 1, is mc squared, okay? So now we go dE dw equals, okay? And what we get here is we get a negative 1/2, and we get mc squared. The negative 1/2 comes from this power here. And then go 1 minus w to the negative 3/2. But since this has dw, or this dw is negative 1, we tack another negative sign on and get that, okay? So now dE dw at w equals 0 is equal to 1/2 mc squared, okay? And then we get 1 to the negative 3/2. So is this going to be right? Yes. Okay, yes, that's right. Okay, great. Now I'm going to do one more term, d squared e over dw squared, because this goes infinitely, okay? And you're going to get a negative 3/4, okay? So the negative 3/2 times this 1/2 gets you negative 3/4 mc squared times 1 minus w to the negative 5/2. But then again, since this dw, or this thing in parentheses, this dw is negative 1, we get the positive sign there, okay? So now dE dw at w equals 0 is going to be 3/4. It's going to be, yeah, 3/4 mc squared, okay? So now what do we get for E when we build up the Taylor series, okay? What we get is, let's see if I can do this over here. We get E equals mc squared, okay, plus 1/2 mc squared w plus 3/4 mc squared w squared plus some terms that are higher order in w, okay? And so what that turns into, let me see if I can move this again. Okay, so we'll just go like that, good enough. Okay. So what we'll get is E equals mc squared plus 1/2 mc squared. And now remember, w is v squared over c squared. So when I take the w, v squared over c squared times this, I get 1/2 mv squared. Okay. Plus, now then I get 3/4. This part doesn't really matter. It's going to be m, and this is going to be v to the 4th over c squared. And then plus some terms that are of order v to the 6th or greater. Okay. That's what this O, this is an O, meaning terms on the order of v to the 6th or greater, okay? These are what are called higher order terms, okay? And they'll all have v to the 6th, then v to the 8th, then v to the 10th, okay? So what do these terms mean? So this term here, okay, is what's called the rest energy. This is the energy that an object has simply by existing, simply by having mass. It has rest energy. Okay? And then what's this term here? 1/2 mv squared. Dude, this is the classical kinetic energy. Okay? This is the kinetic energy that we've used in physics up until now. Okay? 1/2 mv squared. And then these are what are called you call these higher order, okay, higher order kinetic energy terms. Okay? Kinetic energy means energy of motion. Okay? So this here is what we've used for kinetic energy in classical physics. And if V is small compared to C, this is all you need. Okay? You only need this when you're dealing with stuff, and this when you're dealing with stuff that is moving at a significant fraction of the speed of light. So this tells us why we've been able to use 1/2 mv squared for kinetic energy for so long, because it is a good enough approximation, okay, for any realistic purpose where V is not close to C. Okay, so let me sketch out a plot here. Excuse me. Woo. Okay, let me sketch out a plot here of V. This is total energy versus V. Okay, and what you would have is basically you would have this dotted line here represents this dotted line here represents mc squared. Okay, mc squared. And then as you gain kinetic energy, okay, I'll do the kinetic energy in red. Okay, basically this in here that I'm sort of shading red is the kinetic energy, the classical kinetic energy of 1/2 mv squared. Okay, and then if you're dealing with sort of really high speed stuff, you'll see another curve will sort of appear here and get bigger, and this here, okay, is the higher order kinetic energy. So this is the stuff that really only matters when you're up close to the speed of close to the speed of light. And we'll say, just for sake of completeness on my thing, we'll say this here is V equals C. Okay, so these would both this would sort of asymptotically approach infinity, whereas this wouldn't. But okay, so basically, when you're dealing with reasonable values of V, 1/2 mv squared is a good enough approximation. The green isn't really noticeably different from the red there. Anyway, so that's my that would have been my final lecture on special relativity. I think all the videos total come out to about an hour and a half, so that's kind of nice. Hope that was interesting. That's it.